everyone. In this video, we will learn how to represent the relation using matrices. Suppose we have a relation R that is represented from the set A to set B, where set A contains M elements and set B contains N element. The relation R is represented by the matrices form. So first step is always identify what is the order of the matrices. How to identify this? So look at for the relation R. R is defined from the set A to B. It means we will take the elements for the set A as a row wise and the elements for the set B as a column wise. For that, identify how many rows are there. So total rows will be M and total columns are N. So the order of a matrices is cardinality of the set A by cardinality of the set B because the relation is defined from the set A to B. Now the point is what type of entries we have in this matrices. If any ordered pair is a part of a relation, then in place of that we will put 1, and if any ordered pair is not the part of a relation, then we will put 0. It means the entries of this matrices is either 0 or 1, or we can call it as this is a matrices as 0 1 matrices. Now let's understand with the help of example how we can represent a relation in form of a matrices. Suppose that set A contains the element 1, 2, 3, set B contains the element 1, 2. Relation R is defined from the set A to B. So it means R is a relation that is a subset of A Cartesian product B. Now the elements are of this form ordered pair where the first element is from the first set and the second element is from the second set, provided the first element is greater than second element. So here we need to collect all those ordered pair where the first element is greater than the second one. So we have the element in this case as 2 is greater than 1, 3 is greater than 1. Now think for this case, 1 is not greater than 2, 2 is not greater than 2, 3 is greater than 2. So we are getting in this case only 3 ordered pairs with respect to this relation. Now we need to construct its matrix representation. So as per this, the number of elements in a set A is 3. So we can write here we will get the matrix of the order 3 by number of elements in a set B 2. Means there are 3 rows and 2 columns. In order to represent this in a matrix form, first step is label the rows. So in the first row, we will take the element 1, in the second row 2, in the third row 3. And label the column as well. The first column indicates towards the 1 and the second column is for the element 2. Now, relation contain the element 2, 1. First we need to look from the row, then from the column. So 2, 1 means first we will move from the row wise and then for the 1. So 2, 1, this position is containing the element 1. Then we have the element in a relation 3, 1. So 3, 1. Then 3, 2. So 3, 2. And the rest of the elements are zeros. So this is the matrix representation of this relation. Taking one more example, here we have the set that contains the 3 elements A1, A2, A3. B is a set that contains the 5 elements. Now the point is, which ordered pair are in the relation represented by this matrices. So now the matrix representation is given to you. You need to find the ordered pair in the relation. So this is the matrix of the order 3 by 5. and 3 is the cardinality of the set A. It means on row wise we are taking the elements of the set A, that is A1, A2, A3. Number of columns are 5 and the cardinality of the B set is 5. It means we are taking the elements column wise for the set B. As the ordering is not defined, so we will take as it is this order. We will not swap any of these two elements. So from here, collect the ones. So we are getting a first one here. This one represents that R contains the ordered pair A2, comma B1. Means A2 is related with B1. This one gives you the order pair A3, B1. This one gives you the order pair A1, B2. This one gives the order pair A2, B3. This one gives us the order pair as A3, B3. This one represents the order pair A2, B4. And the last one represents the order pair A3, B5. So these are the order pair in the relation R from this matrix representation. Now point is why we are working with the matrices representation of a relation, because with the help of this we can easily identify the type of relation. How? Suppose we need to identify the reflexive relation from the matrix representation. How we can do that? So reflexive relation means if every element of the set is related to itself. Means the ordered pair of this form is a part of relation for each and every element. So if it is a reflexive, in matrices, we will get the diagonal entries are ones. Means if every main diagonal entry is 1, then clearly that represents the reflexive relation. Other entries can be 0 or 1. We will not bother about that one. It can be the part of relation or not. But if diagonal entries all are 1, so clearly that is a reflexive relation. Or we can write in this form a matrix whose all diagonal entries are 1 and rest can be 1 or can be 0. Second is a irreflexive relation that can be easily again identified from the matrix. It means none of the element is related to itself. It means every main diagonal entry is 0. So it's very easy to identify the relation reflexive and irreflexive from the given matrix. If all the diagonal entries are 1, reflexive. If all the diagonal entries are 0, that is irreflexive. Now let's move to the next relation, that is a symmetric relation. Now symmetric relation means if A, B ordered pair is a part of relation, then a reverse should be there for all elements A and B. If it is there, reverse should be there. If it is not there, we will not worry about the reverse one. So now in this case, what type of matrix we are getting? It say that if this entry is 1, then its reverse entry is 1. And if this entry is 0, reverse should be 0 because either both exist or both doesn't exist. What about the diagonals? Diagonal reverse is diagonal entry. So it may be there or may not be there. So it's like if Mij is equal to 1, this implies M of Ji is equal to 1. Or we can say that if M of Ij is equal to 0, this implies M of Ji must be 0. So such type of matrices is basically called as the symmetric matrix. So we can say that if matrix is symmetric means M transpose is equal to itself. This implies relation is symmetric. Now, how to identify the antisymmetric relation from the matrix? Antisymmetric relation means if the ordered pair AB is a part of relation and the reverse is also there, this is only possible when they are equal, otherwise not. Or we can say that if AB is a part of a relation where A is not is equal to B, so this implies reverse ordered pair should not be there. How we can identify this from the matrices? It's like from the matrices, if any entry M of ij position is equal to 1, then its reverse position should be 0, provided we are working with I is not is equal to j, because we are saying that A is not is equal to B. Now what about the diagonal entries? Now diagonal entries can be there or not. Means if AB is a part of a relation, BA is a part of relation, they are equal. It means element can be related to itself. Means diagonal entry can be there as a 1 or 0. But for the non-diagonal entries, if this entry is 1, reverse should be 0. And if it is a 1, reverse should be 0. Now if it is a 0, then it can be 1 or 0. So three possibilities are there. So if it is a 1, reverse should be 0, and if it is 1, then reverse should be 0. Maybe both are not the part of relation. So if the structure we have in a matrix, then it is called as the antisymmetric relation. Whereas in asymmetric relation, we have a similar type of condition that if AB is a part of relation, reverse should not be there. It is also concluding that the ordered pair containing same elements are not the part of relation. It means in a matrices, all the diagonal entries are 0, and if this entry is 1, reverse should be 0, and if it is a 1, then it should be 0, or possibility is there, both are not there. So we will put the condition if m of ij is equal to 1, then mji is equal to 0. Moreover, diagonal entries must be 0. So if this condition is valid in a matrices, then the relation is called as a asymmetry. And the last relation is a transitive, and that cannot be analyzed directly by the help of matrices representation. With the help of matrices representation, we can also find the intersection and union of the relation without evaluating its ordered pair. For example, in this case, we have considered the matrix representation of the relation R1 and R2 on the set A by this matrix and this matrix. So we need to find the union of relation R1 and R2. So for that, first we can write this as matrix representation of relation R1 union R2. This is calculated as matrix representation of relation R1 join matrix representation of R2 relation. Now what do you mean by this? This is called as a join. So it is similar to the OR operator. So when we write 1 join 1, that is equal to 1. Because we are dealing with a Boolean algebra, so it's like 1 or 1 is equal to 1. 1 join 0 is 1. 0 or 1 is 1. 0 or 0, that is equal to 0. So here we need to perform the same operation between these two matrices to calculate the union of relation, but element wise. Let's apply that. 1 or 1, that is 1, 0 or 1, 1, 1 or 0, 1, 1 or 0, 1, 0 or 0, 0, 0 or 1, 1, 0 or 0, 0, 1 or 1, 1, 0 or 1, that is 1. So here we have the matrices representation of R1 union R2 relation. Similarly, we can calculate the R1 intersection R2 matrices representation with the help of these two representation. How? For that, we will take first matrix representation of R1 and matrices representation of R2. We will club them with the help of meet operator. So this is called as a meet operator in the Boolean algebra. So here, when we say 1 meet 1, that is equal to 1, 1 meet 0, that is 0, 0 meet 1, 0, 0 meet 0, that is 0. So this is similar to your AND operator. Apply the same concept but element wise. So first element with the first one, apply this form, we are getting 1. Then same for the other, 0, 1 and 0, 0, 1 and 0, 0. Here we will get 0, 0, 0, 1 and 1, that is 1, 0 and 1 is 0. So in intersection, we are getting a 2 elements. In union, we are getting 7 elements. So this is how we need to calculate the matrices representing R1 union R2 and R1 intersection R2. Not only the representation is helping to calculate the union and intersection, but it also helps to calculate the composite of the function. So here we need to calculate the composite of R and S, that is represented by SOR, because in composite we read from the right to left. So here we have the matrices representation of the R relation and S relation on set A. We need to calculate SOR. So for this, matrices representation of SOR is calculated as. So first we need to operate R and then S. It means first we need to take the matrices of R relation and then with S. But here we will use the Boolean product. This is called as the Boolean product. Boolean product means suppose we have this row 1 0 and we want to multiply this with column 1 1. So when you multiply this, this is 1 into 1 plus 0 into 1. Generally we are writing in this form, but here rather than actual product, we need to do the Boolean product. So 1 meet 1, that is 1, plus 0 meet 1, that is 0. Now 1 plus 0, it is not actually a plus. This is called as a Boolean addition and that is as equal to 1. Basically it is a join. The same concept we need to apply here. So what we need to do? So in the step 1, we have mentioned the matrices represented of the relation R and the matrix representation of the relation S. After that, take the simple kind of a product form. So first row element is get multiplied with the first column element and we have this. Then first row is multiplied with the second one and then third one and we will get same for the next two rows. After writing this, here we will get a 1. This is 0. This is 0. So 1 plus 0 plus 0, that is equal to 1. In this case, it is 0, 0 and here we have 1. So 0, 0, 1, that is equal to 1, 1, 0, 0, that is again is equal to 1. Then 1, 1 and here we have 0. So when you add this one, this is not is equal to 2. We need to add by the Boolean form. So this is equal to 1, 0, 0, and this is 1, and finally we are getting 1 here. 1, 0, 0, that is again is equal to 1. 0, 1, 0, this is equal to 1, 0, 0, 0, and this is equal to 0. 0, 0, 0, and hence we have 0. So final matrix we have in this case as 1, 1, 1 as a first column. Second column is 1, 1, 0. Next column is 1, 1, 0. So this is the final matrix representation of the SOR, that is the composite of R and S. Similarly, we can find the value of R square. What we need to do? We will take the square of this matrices but in a Boolean form, so that you can practice by yourself.